Hello, everyone. Thanks for coming in. I am Alkan, president of the Princeton Society of Physics students. Today, we are extremely happy to host Juan Maldacena with us from IAS. Professor.
Okay, welcome everybody. So I intend this to be more of a dialogue. So I'll be talking here at the Blackboard, and please ask questions at any time, interrupt me, and so on. So we'll be talking about black holes and quantum mechanics. So the first part, I'm going to discuss what black holes are, and then what quantum mechanics implies for black holes. So we'll talk about phenomena like Hawking radiation and black hole evaporation and so on. So when we talk about black holes are a particular space-time. And so it's convenient to draw the space-time represented in some way on the Blackboard. So I'll be spending the first few minutes to explaining how we represent these space-times. So probably you're familiar with the idea of representing space and time as, for example, one coordinate is space, let's say x, and then we have some coordinate which is time, and then each point here represents an event. So for example, a bomb goes off here, so at some point in space and some point in time. And the fragments of the bomb go off to the future, so some move with positive velocity and so on. So presumably, you probably have seen these diagrams. Now, our space-time is four-dimensional, and we will be considering mostly just to draw them configurations that are spherically symmetric. So we're only going to draw the radial direction and time. Okay, so we're going to draw only two dimensions. So for example, we could imagine drawing the time direction t and the radial direction r, and so r goes from r equal to 0 to infinity. And this represents the four-dimensional space-time, where at each point here we have a two-dimensional sphere, and it shrinks to 0 at that position. Very good. Now, space-time is infinite, so it's convenient to sort of rescale, do a uniform rescaling, so that preserves angles, so that the infinite space is represented in a finite region. So this type of diagrams were introduced by Penrose. So this line here represents the r equal to 0 line. That's the same as the line we were representing here. The vertical direction is essentially time, but in principle, time and the radial direction could go to infinity. But we have mapped that infinity to a finite location by doing a rescaling of the whole metric or the whole space-time. And we have done it in such a way that the trajectories of light rays move at 45 degrees. So here, when we were drawing these lines, we could imagine a light ray that, let's say we're going to set the speed of light equal to 1 in this talk, so measure distance in light years and time in years. And so a light ray would move at 45 degrees on this diagram. And we're doing the rescaling in such a way that we preserve the direction of light rays. And so light rays here come from infinity. Well, here it looks like they reflect through the origin, but really they are coming in from infinity at one direction on the sphere and coming out the other direction. So it's just a light ray moving straight in space-time. Okay. Send the light ray later. The light ray comes in and goes off to infinity. So this whole line represents the direction of t equal to minus infinity and r equal to infinity. And here we have t equal to plus infinity, r equal to infinity. So this is this whole line. And different points along this line means light rays that are going to infinity, but started out here at different times. Okay, they get to different points on this line. Okay, very good. So that's this is the diagram of flat space, just Minkowski space. We could imagine the diagram, for example, of a star in Minkowski space would look of a constant radius, let's say the sun, will look roughly like this in this diagram. So because we are doing these rescalings, it doesn't look straight. So if we were drawing it in just the usual coordinates, the surface of the star will look like this. So this is the interior of the star. So here, that's how the star looks like. Now, when we have too much matter in a small region of space-time, then we can form a black hole. So for example, we can start from a very big star and it can start contracting. And in that case, we form a black hole, and the geometry of the black hole is the following. So this is something you can find by solving the Einstein equation. So right now, I'm just going to describe to you the resulting geometry. I'm going to explain its various features. So first of all, the geometry in the future, there is a region where the two-dimensional sphere that we said we were drawing at every point in space-time is shrinking to zero size. Okay? So here, this two-dimensional sphere is collapsing to zero size. Here it was also collapsing to zero size, but this was collapsing in a smooth way. This is just the origin of space, and that's just the coordinate singularity. Singularity is not really singularity. So here, the four-dimensional curvature is perfectly fine. However, here, the four-dimensional curvature is becoming infinite. So really, when we think about curvature in higher dimensions, it's really a full curvature tensor. I'm not going to tell the details to you completely, but so it's a tensor with various indices, and various components of that big tensor are going to zero. That means this tensor sort of tells you what the tidal forces are for. You have two observers that are moving initially parallel to each other. They will be drawn apart or drawn together. And this tensor tells you how they are drawn together or drawn apart. So that's what the curvature tensor is telling us. And okay, so now if you send a light ray from infinity, so let's say we have a light ray that comes from infinity and goes through the origin and goes back to infinity. So that's one possible light ray. Another possible light ray comes from infinity, goes through the origin, and then, well, I guess I forgot to draw the star. So if we had a star, we would have also some surface roughly like this. So this is the star is shrinking and collapsing. Now, there is a particular light ray that when it bounces through here, reaches this point here. So this is a very special light ray or set of light rays because there is one per point on the sphere, right? So this is really a three-dimensional surface. So this is one-dimensional in time and space, and then two dimensions on the sphere. This surface is called the horizon of the black hole. And it separates the space-time into two regions. So there is a region which we call the outside, is what is outside here. So which is so it's a region where if you have an event here, this event can send a signal, and that signal will be received at infinity. Okay. On the other hand, if we have an event here, that event can send signals, but the signals it sends will end up at the singularity, and none of those signals will make it to infinity. Okay. And so this region here we call the exterior of the black hole, and this region here we call the interior. Okay. This is the interior. Now, the horizon is really an imaginary surface in the sense that there is nothing special happening at the horizon. So if you are an observer that is happily moving along, let's say you are an observer that is moving in space-time here, following a time-like trajectory, you don't feel anything special when you cross the horizon. The only catch is that if you cross the horizon, then no matter how fast you decide to travel, so you decide to travel in this direction at the speed close to the speed of light, then you end up at the singularity anyway. And so at the singularity, you will have these forces that we mentioned before, the tidal forces, similar to the forces that deform the oceans in the Earth that will rip you apart and will make you die. Okay? So if you fall in here, you die. In some sense, it's important that the interior of black holes, the singularity is not a point in space inside the black hole. It's a point in time in the future. Okay? So the interior of the black hole looks a bit like a big crunch cosmology. So it's a bit like the whole space-time is contracting, and this two-sphere in particular is contracting and shrinking to zero at this location. So it's a bit like the opposite of the Big Bang when the universe was exploding. Here it's contracting. So the presence of too much matter triggered the collapse of some region of space-time into the singularity. Okay. Now, when do black holes form? So you find that you can solve the vacuum Einstein equations. First, let me describe to you a bit more the geometry outside the black hole. So this geometry outside the black hole is, this geometry in the region where there is no matter is a particularly simple geometry that was found soon after Einstein wrote his equations. So the equations here in the vacuum roughly look like some curvatures. This is some curvature term, so I don't have to understand exactly what it means. It just means that some average curvatures should be equal to zero. And you solve these equations, and you find a particular solution. And that I'm going to draw only a piece of that particular solution, and then I'm going to draw the rest of the solution later. So it has this future horizon region, and it's time symmetric in the past, so there is also horizon here in the past, and then it has some singularities here in the future and here in the past. So this is a solution with no matter. Here is the solution of a collapsing star which contains matter. So these two solutions coincide in this region outside the matter. And the space-time has can also be represented. I'm going only to draw the spatial dimensions. So the horizon, which I was drawing in blue, you can view as some kind of sphere. So this is now I'm trying to plot the three-dimensional space-time. And this has some characteristic size, which is what we call sometimes called the Schwarzschild radius, or the typical size of the black hole. And if you solve these equations, they have no matter, there is no particular scale. Curvatures go like 1 over the size. And so if you rescale the solution, you make it bigger, this thing will be rescaled, but it will continue to be 0. So we'll have solutions with all possible sizes. And there is a connection between the mass and the size. So g Newton times the mass is proportional to, there are some factors of 2 that I'm not writing. And there are factors of the speed of light, which I'm setting to 1. Okay, so the black hole will form if you put matter, an amount of mass in a region. So suppose you start with a certain amount of matter, a certain mass, okay, and you put it within some size r, which is smaller than the left-hand side. Okay, then that will collapse into a black hole, and from the outside you will have a black hole. Okay. When will that happen? Well, imagine you have matter with constant density, right? So this left-hand side would go like g Newton times m, and that would be rho times radius cubed of the, so that, this will go like radius cubed, okay? And then we should compare this. So the question is when this quantity will become bigger than the radius r, right? The radius r where it's sitting. If it is bigger, then it will collapse to the black hole. So one interesting thing that you see here is that if you take any density of matter, no matter how small, and you make it bigger, you make a bigger and bigger ball of that, that eventually will collapse into a black hole, okay? So if you take some density, let's say the density of air, you make a big ball of air, very, very big. The size of this, I think, works out. Well, you can do the calculation, so don't trust my word now. But if it is roughly the size of the solar system, it will collapse to a black hole. Okay? And that's how we think black holes at the center of the galaxies were formed. So you can have densities of initial gas compared to air in a region the size of the solar system that could collapse to a black hole. If you take the highest densities that we can imagine with ordinary matter, those are the densities in nuclear matter inside the nucleus. So you put a bunch of protons together, neutrons, preferably together, lots and lots of neutrons, you form a neutron star. When that is bigger than about a few kilometers, you will form a black hole. So if you have higher density of matter, you will form the black hole at a smaller size. When you have lower densities, you will form it at a bigger size, but you will form the black hole. Okay. And theoretically, you can discuss black holes also that are much smaller. You could imagine that you have a much smaller black hole. It will be difficult to produce it in any practical way. But as solutions of the equations, they exist as mathematical solutions. Whether they can be formed through some practical means or even whether they were formed through some natural means in the universe somewhere, we don't know. But they are possible configurations. Are there any questions or comments you want to make? Yeah. Yeah, so the diagram in the top right, maybe I'll draw the full diagram, so maybe we'll make this discussion a little more clear. I will discuss it a bit more in detail. So you take Einstein's equations, and you find a spherically symmetric solution. Okay? And then you draw the space-time diagram that corresponds to that spherically symmetric solution. Yeah, so the question, I will repeat the question. The question was, what did this diagram represent? Okay. And so it's representing a solution, the simplest solution of Einstein's equations. So you take Einstein's equations with spherical symmetry. It was the first exact solution to be found. And it's a space-time that has the following shape. So let me, well, all these lines should be 45 degrees. Sorry for my bad drawing abilities. It has some region here, which asymptotically or far away looks like four-dimensional Minkowski space. So this is four-dimensional Minkowski space, the same space we have far away in all these pictures. Okay. This side here is also another separate four-dimensional Minkowski space. These blue lines are surfaces where the size of the sphere that we are not drawing has constant size and represent horizons. Okay, so regions that separate events that are in here cannot send signals to the outsides, while events here can send signals. Okay, so that's the solution, and it represents two black holes in two separate universes that are connected through the interior. Okay, we'll discuss these geometries a little bit more later. And for now, let me just say that when you have a black hole that forms in the universe, so a black hole that forms from natural processes, what you will get is a geometry of this kind that will, in this region outside, that will be a portion of this geometry. So that will be, let's say the star was doing something like this, right? This is the surface of the star. Outside the surface of the star, you have a portion, this solution. Inside the star, you have a different solution because now there is matter. You have to solve the equations that you have to solve are different, and you have a geometry which looks locally here near r equal to 0 as the geometry of flat space. But well, it's a curved space with the matter distribution and so on. So this is the geometry of a collapsing star. This is the geometry of a mathematical solution that was found, more than 100 years ago. It was understood that it had this geometry only quite a while later. There was a lot of confusion about the solution. So initially, it was thought that that the solution was singular at these locations, so that because they chose some coordinate system that was not convenient. And Einstein himself thought that there was a singularity. So there was a lot of confusion. It took about 50 years to understand that this was the correct diagram. It was actually understood by a Princeton student, by the way, Martin Kruskal. Yeah. Yeah, this is the Schwarzschild solution. Okay. Yeah. I guess Schwarzschild means black shield, and the horizon is a black shield that doesn't let you see inside. So the name of the person was chosen. Okay, anyway, that's a bad joke. Okay, now. Okay, we'll discuss that a little more, but before we discuss that, I would like to discuss one other thing. Okay, so black holes, of course, they started as confusing mathematical solutions, as we were saying. Then it was understood that they could form through the collapse of stars, and are now there is a lot of evidence that there are black holes in the universe. There's a black hole in the center of the Milky Way. There are black holes that collided and emitted gravity waves. I'm sure you heard about that. There are pictures that are taken by the Event Horizon Telescope of the region near the black hole in a nearby galaxy, and you see the light coming from a region very close to the black hole horizon. So now I think we are living in a time where the study of black holes is a hot experimental topic with lots of results and lots of exciting evidence for the existence of black holes, and lots of detailed studies are being made of observational aspects of black holes. Okay, so I will not discuss any of those observational aspects unless you have some questions about any of them. Yeah. Yeah. No, I don't anticipate that. So, I mean, there are some people that say that they're good, but if our understanding of gravity is more or less correct, we don't expect that quantum gravity effects should be important for those black holes. Of course, if some quantum gravity effect was found, then it would be a big departure from, I mean, yeah, it wouldn't be what it's normally called conventional quantum gravity. So, yeah, because the quantum gravity effects are expected to appear at short distances. So Einstein gravity is a theory where as you go to longer distances, the metric of space-time has less and less fluctuations. And as you go to shorter distances, it has bigger and bigger fluctuations. That is, well, I'm not sure whether I should explain it. If you want, I could explain it in more detail why this is the case. But there is a distance called the Planck distance, which is given by the square root of g Newton times some powers of h bar. So this is in units where h bar is equal to 1 and c is equal to 1. And this distance is 10 to the minus 35 meters. So it's a very tiny distance. So like the smallest distance we can observe today with the best microscopes, which is the Large Hadron Collider and Accelerator in Geneva, is about 10 to the minus 18 meters. Okay? So it's much, much smaller. So it's twice. So if we're halfway. So you could say we are halfway to the Planck. But this is at this distance. If you had a black hole of this size, it would behave very quantum mechanically. Okay, we cannot describe it using Einstein's equations. But a black hole which is bigger than this size, and in particular astrophysical black holes are much, much bigger than this size, we could describe using Einstein's equations. Okay. Very good. Now I'd like to discuss a phenomenon, a surprising phenomenon that occurs with black holes once you include quantum mechanics. So we are going to include quantum mechanics in its sort of relativistic form. So what is relativistic quantum mechanics is the theory we use to describe particle physics. So particles that move at the speed of light and so on, they are described by a form of quantum mechanics. It's just, if you wish, it's a special version of quantum mechanics that can describe these interacting particles. And this type of theory can be considered in flat space. So we normally think about it in flat space. For example, if we are thinking of an experiment in a collider where you have protons that collide and give rise to other particles and so on. But you can also consider it in curved space. So you can consider this quantum mechanical theory in curved space. And when you consider it in curved space, in particular in the curved space of a black hole, there is an interesting effect that happens. So I'll summarize it. So the effect that happens is that the black hole appears to emit particles, radiation, at some finite temperature. Okay? At the temperature that is of the order, so again in units where the Boltzmann constant and h bar and c are equal to 1, of the form 1 over the size of the black hole. Now what this means is that if you have a black hole with some size rs, right, Schwarzschild radius rs, then the typical wavelength of radiation, so let's say of light that comes out of the black hole, or radio waves, or whatever it is, has a wavelength which is of order the size of the black hole. So the typical wavelength would be this wavelength, okay? So of course, you can also emit longer wavelengths, but the peak wavelength in the thermal spectrum will be of this order. So like smaller wavelengths will be emitted much less. Very good. So I'll try to give an explanation for why this happens in a moment, but let me just try to make this effect a little more clear. For astrophysical black holes, this effect is very, very small. And the reason is that, and undetectably small. The reason is that astrophysical black holes are of the size of a few kilometers or bigger. And so the temperature is very, very small, smaller than the temperatures of the matter that surrounds the black hole. For example, smaller than the temperature of the cosmic microwave background. So you're never going to see this effect in astrophysical black holes. Okay. Now, what could you see if the black hole was smaller? So imagine, question. Well, first of all, you see from this formula that if the black hole becomes smaller, the temperature becomes higher. And at some point, it could become so high as, let's say, the surface of the sun. So such a black hole, you would see, like you see the surface of the sun. So you'll be able to see with your own eyes, okay? You'll see it of a red color first, and then white as you make it smaller and smaller. The question is, how big should a black hole be for you to see it white? Right? Any guess? Okay, that's one guess. So what is the wavelength of white light? Number. Size of the proton or bigger? Is it bigger than the size of the proton? Yeah. Is it bigger than the size of an atom? Is it the size of a bacterium? Yeah, size of a bacterium. Half a micron, okay, roughly. So if you have something that was the size of the bacterium, half a micron, let's say, or something a bit smaller, you would actually look at it and you would see it white, okay? So this, I think, the fact that you would see it white shows that the effect is surprising, right? So black holes were called black because everything would fall in and they would not even let light escape, right? But now we are seeing that quantum mechanics implies that certain black holes will look white. Okay? So that tiny little black hole, it would be very small, right? The size of a bacterium, so there wouldn't be much light coming out of it. So you would barely see it, but you would see it. By the way, you can calculate how heavy that black hole would be, and it would be actually very, very heavy. So, like the mass of a continent. So you don't want to be very close to it. Okay, anyway, so that's just some orders of magnitude of this temperature. Okay, let me just explain a little bit why we think that this, well, why, so this is an effect which has never been seen in black holes, as I mentioned, but it's predicted theoretically. So it follows from the basic principles of quantum mechanics and relativistic quantum physics. And the basic observation is that if you have, let's say, some light rays that come in here, you see that two very close by neighboring light rays would suffer drastically different fates, right? So one that is just outside the horizon will eventually make it out and will come out of the black hole. So this is a light ray that is moving radially outwards, right? So moving outside the black hole, eventually will make it to infinity. The other one will go to the singularity. So they diverge in the trajectories. Now, a quantum field is basically like a collection of harmonic oscillators, all next to each other and interacting in some way. Okay? That's roughly what a quantum field is. And these diverging trajectories are separating neighboring harmonic oscillators. So if you imagine you have two harmonic oscillators, let's say this is one harmonic oscillator, and you have a second harmonic oscillator, and they are close by, so there is some interaction between them. And so if you look at their ground state, so their state of minimum energy, it will not be the same as the ground state for a single harmonic oscillator. So if you have two separate harmonic oscillators, well, each one will have its ground state wave function. If there is some interaction, the ground state will be slightly different. And if you suddenly, let's say, turn off this interaction, so you are still left with the ground state of the interacting system, from the point of view of this other, let's say, non-interacting system, it will look like an excited state. It will not be the ground state. So it will be a combination of the ground state and the excited states of the neighboring harmonic oscillators. Now, this process of the two particles diverging and separating is similar to turning off this interaction. And for similar reasons, one of the harmonic oscillators sort of falls in, the other one remains outside, and that's, but it's not left in the ground state that it would have if it was not interacting. So it's left in some excited state, and that excited state is what we then perceive as radiation, eventually perceive as radiation coming out. This is sort of a qualitative explanation. There are other qualitative explanations which are similar to this, which you might have heard before. You can think of the vacuum as constantly emitting pairs or pairs of particles that are being created and destroyed. And then if a pair gets created here, one of the members of the pair can go in and the other one can escape to infinity. This explanation of the harmonic oscillators, I like it a little more because it's a little closer to the actual calculation. It's not identical to the actual calculation. Okay, so that's an interesting effect. And I should mention that this effect is present whenever you have a horizon. And a situation where you have a horizon also is in the early universe. So in the early universe cosmology, if the universe was inflating, so in cosmology, people propose that at the very early stages, you have a period of so-called inflation. So a period where the universe expands with a constant rate, with a very high expansion rate for some time. And during this time, the universe is expanding so rapidly that you can only see a small portion of this universe. So there is a kind of cosmological horizon, similar to this black hole horizon. And for the same reason that we see this Hawking effect here, we see also a similar effect, so we see some temperature in this universe. And we think that that temperature is the origin of the initial perturbations in the density of the universe. So if the Big Bang had occurred and the universe was exactly uniform in the very beginning, the universe was very close to uniform in the beginning. If it was exactly uniform, it would be uniform still today. So there would not be planets, stars, or anything like that. It would be just a uniform gas, like hydrogen atoms and radiation. But the universe wasn't exactly uniform, and there were some initial fluctuations, and we think that, so the current best explanation of this is this period of inflation, including this Hawking-like effect that produced these perturbations, and then those perturbations grew to form galaxies and stars and the planets, etc. Okay, so even though this effect in the context of black holes has not been observed, the similar effect in cosmology is thought to be crucial for explaining some feature that we see in the universe today. Okay? And this also shows the interrelation of the study of black holes and cosmology. Sometimes something you learn in the context of black holes then has some application for cosmology. And for this reason, many of us have been studying quantum aspects of black holes, not because they were going to be observed in the gravitational wave observatories, but we are studying them as a kind of stepping stone for then understanding perhaps aspects of cosmology that I would say that cosmology is probably the best bet for observing some effects of quantum gravity. But black holes are in some sense a little simpler to study because in the case of black holes, we could sit far away where there is no black hole and the universe is pretty solid and not fluctuating and at long distances. And from there, we can send in waves, imagine sending in waves and setting up thought experiments to try to understand the theory better. So the objective of the study of quantum aspects of black holes is to understand the theory, understand what the theory predicts and how to put together quantum mechanics and gravity. Okay, so let me say a few more things that this formula implies. So we had seen the formula for the mass of the black hole, which hopefully is still here. So we know the mass, and knowing the mass is the same as knowing the energy, right? Remember E equal to mc squared. And so we know the energy and the temperature, and then that implies that we can calculate the entropy. There is a thermodynamic quantity called the entropy that we can calculate if we know the energy or the mass through this formula. So a small change in entropy should be equal to a small change in mass divided by the temperature. So that's, if you wish, the thermodynamic definition of entropy. And we can calculate this entropy. So dm is dr, and temperature goes like 1 over r. So we get something after integrating this is proportional to r squared, factor of g Newton in the mass. So this ends up being the area of the horizon divided by 4g Newton. Okay. G Newton, remember, is this L Planck, which is 10 to the minus 35 centimeters. So this is a very tiny distance. Okay, so it's area divided by tiny distance squared. So this is a unit of area. Here I've set h bar and c equal to 1. If I hadn't set h bar, there is an h bar here in the denominator. So again, it's an effect that goes to infinity when h bar goes to 0. I guess also here in the temperature, if I had left the h bar should be here. So it's a quantum effect. Okay. So black holes have this entropy. And this is a surprising formula that was initially conjectured by Bekenstein, and then later Hawking found the entropy, found the temperature, and then now, well, I didn't do a historic derivation of this, but more conceptual derivation of this formula. Okay, now why is this formula interesting? This formula is interesting because it's telling us that the black hole started its life as some kind of classical solutions, right? So ordinarily, classical solutions of classical equations, they don't have any entropy, it's just one solution, okay? So if you take electromagnetism and have, let's say, some wave, just a single wave propagating in your space that has zero entropy. Okay? But here we're learning that a black hole has a very big entropy. Okay? And this entropy is bigger than the entropy of any object that, so if you have some object that is occupying some space surrounded by a certain area, that the entropy of that object should be smaller than this area. Okay? Should be smaller than this. So this is somehow the maximum entropy for any system within this area. And it's telling us that the black hole is a thermodynamic object. There are some moving parts to the black hole. So entropy in physics comes from the motion of some microscopic constituents. So if you have the entropy of air, for example, or the temperature of air, we explain it in terms of the motion of its constituents. So one question is, what is moving inside the black hole? And black holes have this entropy and these properties independently of how you make them. You can make black holes out of matter. You could imagine focusing gravity waves in a small region of space and form a black hole out of gravity waves. So without any matter, just purely the vibrations of space-time itself, you can form a black hole. And independently of how you form the black hole, you derive that, well, it will have Hawking radiation, it will have this entropy. And also, this entropy only depends on G Newton. I didn't need to tell you any properties of matter. I didn't need to tell you what the electron mass is, the charge of the electron, and so on. Quantities which are very important for determining the properties of matter. So we think that this entropy has to do with the very constituents of space-time. So somehow, when you form a black hole, the degrees of freedom that give rise to this entropy should be, if you wish, the atoms of space-time, whatever elementary constituents of space-time we have. And we got some window into them through these formulas. Okay. Are there any questions about this? Yeah. Yeah.
Like white black hole.
Yeah.
To probe quantum gravity, we have to the Planck scale, right?
Yeah.
Which is much smaller than a proton.
Yes, yes, yes.
But then at the same time, black hole the size of a
Bacterium, yeah, that's right.
bacterium,
Yeah.
then we
Wonderful. Yeah. Very good question. So the question is, I said before that to probe quantum gravity, you need to go to the Planck scale, while here we are seeing some quantum aspects of black hole. So these quantum aspects of black holes are not directly related to quantum gravity, in the sense that it's electromagnetic radiation, for example, that we see from black holes, and it depends on the properties of matter. It's and that's why we can calculate it. So we can calculate it because we can, the fluctuations of space-time itself are relatively small and are under control, and you can do the calculation. So the Planck scale is where our current theory ceases to be valid. So this Hawking radiation is an effect that occurs because we have a curved space-time, and we have quantum fields or quantum matter moving that curved space-time. And that is sufficient to derive Hawking radiation. I mean, of course, the black hole also emits gravitons. It could also emit gravity waves. And those can also be computed in this approximation when the radius of the space is very big, when the curvature is small, and the size of the object is big. You can treat the gravitons as particles that move on a fixed geometry, and you can do a control calculation. You don't need to have any complicated theory of quantum gravity. You can do it within the standard theories we use for particle physics, the standard approximations, let's say. Was this answer clear to everyone, or any other question or comment? Okay, so let me see. I had here another feature, another point about the temperature. Well, I guess I'm running out of time. So, well, maybe I should mention it anyway. So we have a person in Minkowski space. So there's an effect similar to the Hawking effect. It's sometimes called the Umru Effect. Where now I'm going to draw the usual space-time diagrams. And we're going to imagine someone who starts here at some position, let's say some distance r from the origin, and starts accelerating, okay, with constant acceleration. Eventually, they will move at the speed of light, okay? And similarly in the past, well, I don't know, that doesn't matter what it does in the past, but if it starts accelerating with constant acceleration, then it turns out that this person will also measure a temperature. Okay? This is also a bit surprising. That you are in a space-time, in flat space. The flat space is at 0 temperature. I mean, if you are moving with constant velocity, for example, if you're stationary or you're moving with constant velocity, and you hold the thermometer here, you would measure 0 temperature. However, an accelerating observer would see a non-zero temperature, which will be equal to the acceleration. So the formula, temperature, equal, there are some factors of 2 pi that I'm not writing, equal to the acceleration. And also there are some factors of c that I'm not writing, so c equal to 1. Now, the factors of c are important. So for example, if the acceleration is g, the acceleration of gravity, then and there's some factor of c squared, which, well, first of all, the temperature would be very tiny. And we can translate the temperature to a wavelength, and the wavelength is roughly the distance of your horizon. So notice that this person who accelerates with constant acceleration will see a horizon. How far this horizon is from the initial point depends on how high this acceleration is. So if you have a trajectory that passes closer, that will have a much higher acceleration. Okay? And the temperature is basically 1 over this r, so 1 over that distance. Okay? So for example, if you were accelerating with the acceleration of gravity, so you get yourself in a rocket and you accelerate at the maximal acceleration you can withstand, which is roughly g or maybe 20 g. You accelerate at this velocity, at this acceleration, sorry. This distance is about a light year, okay? So that implies a very, very tiny temperature. So you're not going to be able to see this effect by accelerating at a normal acceleration. Of course, if you put a particle in an accelerator, and then you can accelerate it to accelerations which are big enough that you could see some effect, and it is seen in some accelerators. Okay, so this effect is closely related to the black hole one, because this region here near the center of this diagram, it looks basically like Minkowski space, so it looks like flat space. And an observer who's following this accelerating trajectory would be an observer who is at a constant proper distance from the black hole horizon. Okay? So an observer sitting at a constant distance from the black hole horizon, so some observer here in this diagram sitting here, of course feels a force towards the black hole, and if he wants to stay stationary, will have to, he's accelerating, right? And would also measure a temperature, and this temperature is related to this Hawking temperature we're discussing here. Okay, very good. Any question about this? Okay, wonderful. Now, these developments have led to a certain hypothesis, and this hypothesis we've called it a central dogma. Okay, so it's a central hypothesis. In the same way as biologists have their own central dogma, we have our central dogma, which says that if you are looking at a black hole from the outside, so a black hole from the outside, can be replaced by a quantum system with S qubits, where S is the area over 4G Newton qubits. So this is really a statement about the dimension of the Hilbert space. So in quantum mechanics, well, I'm not sure how familiar you all are with quantum mechanics. So in quantum mechanics, the basic, who's familiar with quantum mechanics in this audience? Relatively small portion, okay. Well, quantum mechanics are the kind of laws that we use to describe small systems like atoms and molecules. And in this kind of mechanics, we have that observables are observable quantities, like let's say the spin of a particle and so on. They live in a certain space, sometimes called Hilbert space. And those observables are represented as matrices, as n by n matrices. And so it's important when we talk about a quantum system to say in what kind of dimension it lives. So how complicated is this space? So for example, the simplest system is an electron spin that lives in a two-dimensional space. Okay? So S here is the logarithm of the dimension. So, and a qubit is like is the simplest degree of freedom, like an electron spin, and you can have many of them, and the number would be this number. Okay? They all can interact with each other in some arbitrarily complicated way in principle, but the statement here is that this number is finite. It's not infinite. Okay? That's one part of the statement. Second statement is that it evolves according to the laws of quantum mechanics. So quantum mechanics says that there is a deterministic evolution for the wave function. So the wave function is some concept in quantum mechanics. And there is something called the Hamiltonian that evolves the system. And so it evolves according to standard evolution. And that this, so the statement is that if we do experiments of the black hole as seen from the outside, so what experiments can you do? So you can send in a particle, and then you can look at the Hawking radiation that comes out. Notice that the black hole can evaporate completely. So as you emit Hawking radiation, the black hole will start getting smaller and smaller, and it will lose its degrees of freedom. But the idea is that all this process is in principle calculable through some quantum system. This hypothesis does not tell you what the quantum system is. So it only tells you that some quantum system like this exists. Okay? And this is non-trivial. I mean, it's not obvious from the space-time diagrams that we normally draw. So, for example, naively, you can start from a black hole. You could start from a black hole and send in, let's say, pure matter, so matter in a very specific state, and in such a way that it evaporates, but it never loses mass, right? So we constantly keep feeding matter. And that system would start producing lots and lots of entropy. But if it is a standard quantum system, we cannot produce an entropy which is bigger than this, for example. And so it becomes a non-trivial statement. And so many of us have been studying questions around this, trying to understand whether this is true or not true. So some people argue that it's not true. Hawking famously argued that this is not true. So had a paper saying that it cannot be true, presenting an argument basically very similar to the argument I just made of the process of forming the black hole and letting it evaporate. Then, well, many of us studied this in detail and found some more evidence that this could be true. In fact, then Hawking retracted his original position. But then other people found some new paradoxes and some new problems. And the conversation sort of continues. And I would say that now we have more evidence that this is correct, but understanding exactly what this quantum system is something that we don't know in general. Okay, okay, very good. So this could look perhaps a little abstract, but the goal of trying to understand this is trying to understand what the rules of quantum gravity itself is. So let me just tell you a little more of what Hawking's picture was, because it's interesting. So he said, well, let's imagine the space-time diagram of a black hole that forms and evaporates. We expect that space-time diagram roughly to be of this form. So we have the initial black hole that collapsed, right? And then it evaporates, it emits Hawking radiation. Eventually, its size becomes smaller and smaller until it becomes of very small size. When it's of very small size, we get to the Planck scale. We don't know exactly what happens, but by that time, the black hole will have very small entropy and very small mass. So we assume that nothing very dramatic happens, that maybe you emit a few quanta, and then you get back to flat space. And this portion of the diagram here, this is R equal to 0 in flat space. So we collapse the black hole, and eventually we end up with flat space full of radiation. And the picture of the people who don't believe in the central dogma is roughly something like this, that we started with some universe, if I can draw this properly. We started with some universe, the original universe, and then we threw in matter and so on. And we are left with a second universe, which would be this whole region here that collapses, okay? That got disconnected from the original one. So here, we get back the original universe. And this looks like we maybe could be emitting a so-called baby universe. And from this picture, it would not be unreasonable to think that entropy can flow in here and that you can lose information, okay? And so that was also part of the reason for Hawking and other people who proposed such ideas. And so the question is how to make these type of diagrams or these type of ideas consistent with the idea that from the outside, if you look just purely at the parent universe, you can replace this whole black hole and so on by some relatively ordinary quantum system. Okay? And understanding this is, well, yeah, understanding fully would be tantamount to understanding really quantum gravity. I think we will learn something important about quantum gravity by understanding it completely. Now, perhaps I should, well, I will end by giving you a flavor of the kind of quantum systems that could describe such black holes. And I'm going to tell you about a very simple one. So to study this question in more detail, one needs to, well, at least with present technology, we don't know how to do it for a black hole in the standard model that exists in nature. So we work with idealized theories of quantum gravity, so some so-called string theories in 10 dimensions. So these are, if you wish, simplified toy models of quantum gravity. We don't know whether they describe nature or not, but for the purposes of, they also contain black holes, so we try to study them in those models. So there is some particular 10-dimensional black hole, charged black hole, that can be described as a collection. So we start with a bunch of harmonic oscillators. So imagine you have many harmonic oscillators with some interactions. So some x to the 4th interactions. They all interact with each other in some complicated way that I'm not writing. And there are also some fermionic oscillators. If you don't know what fermions are, don't worry about it. So, and if these interactions are large enough, and they are basically like an anharmonic term, but they are strong, then it could describe this system. Okay, and if you excite thermally this system, you can compute the entropy. It's not trivial because there are some interactions. The interactions are important, but you can do it with a computer numerically, and you find that it agrees with the area formula that you can compute on this side. And like this, there are many concrete calculations that you can do, and you can analyze for comparing these two types of systems. And now an important property of the quantum system that we should have is this quantum system should have strong interactions because strong interactions mean that when you send in a perturbation, the perturbation will thermalize quickly, will disappear. And the perturbation thermalizing is equivalent to some object fall into the black hole. Okay? So the fact that things can fall in and they don't come back out is related to things thermalizing and mixing. Right? The same way that if you drop some ink into a glass of water, the ink will dissolve into the water, and you will not have the droplet of ink then coming back out. Okay? Even though in principle it could, but it just does not do that entropically. And the stronger the interactions between the water and the ink, if you did that in a gas, it might take a little longer. When the system interacts strongly, then that will mix more quickly. Okay, so, and finally, I should mention that thinking about these problems also was useful for people who study interacting particles, for example, in condensed matter physics. So there are some systems in condensed matter physics or systems you could, in principle, perhaps in the future, manufacture using quantum computers or quantum simulators that will display properties that are somewhat similar to black holes. And the connection to black holes can be useful for analyzing those systems. Okay, maybe I'll finish here and I'll continue answering questions if you want.